on, people started to theorize that maximum shear stress failure theory might be a thing based on how tensile specimens looked when they broke. People noticed that they very seldom broke on planes that were perpendicular to the direction of the applied force, like you would expect. You would normally expect, or at least I would, if it broke on any other plane besides one that was perpendicular to the direction of the applied force on the specimen, you basically have bigger amounts of area that have to fail in order for it to fail in that way. And yet they would never, very seldom would they break on planes that would be, more or less perpendicular to the direction of the applied force, and instead they would tend to break on planes that looked like they were closer to 45 degrees relative to the direction of the applied force. People started looking at that and saying, well, maybe, given the fact that when we do a stress transformation, our maximum shear stress occurs on planes that are 45 degrees tilted relative to the direction of the applied force, maybe the actual mechanism of failure has more to do with shear. Okay? So that's kind of the background, and I talked a little bit more about that in the lecture that I have posted. But from there, we're going to go ahead and get started with this idea here. All right, so the maximum shear stress failure theory states that when the overall maximum shearing stress applied to a part in service reaches the amount of shearing stress that would cause a tensile specimen of the same material to fail, we will predict that the part will fail. All right, and I think we've even done a couple of these so far in here where you've had to sort of think about this maximum shear stress that's present in a part that might have multiple axes of loading, right? And the reason that's important is because that feeds into this failure theory. And we're going to look at a few of the possibilities that could exist that kind of would create this maximum shearing stress, okay? So for the first one, let's think of the first case being, what if, where sigma A and sigma B are in plane principal stresses. So imagine that sigma A and sigma B would be like the stresses that you would measure with maybe a strain rosette or something on the surface of a part. Plane stress is often the state of stress that occurs on the surfaces of parts, and so it's often the state of stress that you have, plane stress, it's often the state of stress that you have at a location where you might have critical stress, meaning the place where a part is going to fail first. So if both of these in-plane principal stresses are positive, what would that look like on a Mohr three-circle diagram? Okay, so let's say this is, the kind of some axes here where, since it's a Mohr diagram, it's going to be normal stress and shearing stress. And so if we have sigma A and sigma B being my in-plane principal stresses, that means I can plot those, and one might be bigger than the other. So let me just say, let's say sigma A, for at least for how I'm sketching this, is bigger than sigma B, but they're both positive. Okay, what would Mohr circle look like for the in-plane stress? Okay, something kind of like this probably, right? Okay, so that's where we would start, but that's not, that circle right there, the kind of the radius of that circle does not yet describe the shearing stress that would be the maximum overall shearing stress, because why? You have one more principal stress, and because it's plane stress that we're talking about here, that third principal stress is going to be 0, right? And so there's this other circle that will exist here, something like this, right? And so what is the maximum shear stress going to be for that circle? Okay, sigma A is going to be the diameter. Since it goes back to 0, sigma A is the diameter of the circle. So the maximum shear stress is going to be what? Right. It's going to be sigma A over 2. Okay. Well, before I go into my other cases, let's actually now take this information and use it with my definition of maximum shearing stress, failure theory. It says we're supposed to take that and compare it with the conditions that exist in a tensile specimen when it fails, right? When it yields, right, is one form of failure, right? So let's go down here and look at a tensile specimen stress condition, okay? If you had to give it a name, what would you call the stress condition of a tensile specimen? Okay, and I'll give you some maybe multiple choice. Would you call it uniaxial, biaxial, or triaxial for a standard tensile test? Uniaxial. You're only pulling on it in one direction. You're not twisting at the same time. You're not trying to pull in multiple directions at the same time. You're only pulling in one direction. And if you're saying that it takes a value of, let's say, S sub y to yield the material, okay, where would I plot that on a Mohr circle? Right? Since it's a uniaxial state of stress, what we would say is that I have one principal stress then that would be that value, right? S sub y. And what are my other two principal values? Both of them are 0. Okay? So if I think about what the Mohr circle would look like for a tensile specimen that I load up to the point where it yields, right? It's going to look something like this for the Mohr circle. So my question is, what is the shearing stress? Because go back and look at the definition that we had up here. The overall maximum shearing stress applied to a part in service reaches the amount of shearing stress that causes a tensile specimen of the same material to fail, right? We predict that the part will fail. So that's saying we need to figure out what's the amount of shearing stress that exists in the tensile specimen, not the amount of normal stress that we're actually applying, right? So when you apply the normal stress, it induces a shearing stress in the piece of material, and we're asking, you know, what is that going to be? And so what will it be? Okay, so the tau that you're going to have here, okay, maybe I'll say tau max here, is going to be equal to S sub y over 2. Right? And so what I would say out of this is that we should be able to have a statement about you know, how does sigma A compare to S sub y right at the point where we predict failure? Right? We just equate these two, right? We have, this is the maximum shearing stress that exists in my actual part in service, and we're saying if it's about to fail, then it's got to be equal to this tau max is equal to S sub y over 2 if, you know, for our maximum shear stress failure idea, right? So that tells me then that sigma A over 2 is going to be equal to S sub y over 2 at the point of failure. Or what can I do with the over 2's? We can just get rid of them. So we basically say, you know, if we're going to interpret that in words, what we would say is we just look at the larger of the two in-plane principal stresses, and when the larger of the two in-plane principal stresses reaches the yielding strength of the material, we predict failure. Okay? That's if both in-plane principal stresses are positive, right? That's where we started out with this little discussion. So what I can do there is I can say on a little set of axes where I look at my values that I might have of in-plane principal stresses, I just took care of this upper right quadrant, right? I said, you know, as long as both of them are positive, okay, imagine plotting on here, say a location right here that is my yielding strength, okay, and let's say that sigma B is less than sigma A, right, then I would have values in this sigma A, sigma B, plane that it doesn't matter what my value is of sigma B. I'll just kind of draw a line right here, and whenever sigma A goes to the right of that line, I predict failure. Do you agree? Like if it's to the left of that line, we say it's not going to, we don't predict that it will yield. But if it goes to the right of that line, we predict that it will yield. Okay? But that only goes up so far, right? Because at some point, sigma B might be larger than sigma A. See that? And so how high would this go to the point where I would say, you know, where am I going to end up with a problem with stress in my vertical direction. You know, again, up to S sub y. So my point is, you can have any values where both sigma A and sigma B are positive, right? And anywhere in this range in here, we're saying we're safe, right? Anywhere outside of that range, we're saying we're going to predict yielding when I've got a biaxial state of stress where both of my principal stresses are positive. Okay? With me so far? Okay, well, what's my possibility I could have for case 2? Okay? For case 2, I've got sigma A and sigma B have opposite signs. Okay? Again, this is for Mohr Circle. And I should probably move my stress, or my shearing stress axis. Okay? If I have my in-plane stresses set up so that I have one that's positive and one that's negative, okay? So that'd be, let's say that's sigma A and that's sigma B. My in-plane stress, Mohr circle, would look like this. Okay? And where's my other principal stress after I've taken care of my in-plane principal stresses? 0, again. Well, that just sets up a situation where I can look at either of those two other circles on Mohr's 3-circle diagram. Those do not have a bigger radius than the first circle I drew. Okay? And so what would we predict in terms of the maximum shearing stress in that case? Okay, yeah, so my maximum shearing stress is going to be equal to sigma A minus sigma B over 2. Okay, and, you know, what would be my condition where I would predict yielding? Sigma A minus sigma B over 2 would be equal to Sy over 2. Or again, we could just say, we'll cancel out those over 2's, and we'll just say sigma A minus sigma B would be equal to Sy. Okay? Now, let's think about that, that as an equation. Okay? Let me actually plot, since I've got sigma B on the vertical and sigma A on the horizontal, let me plot that as if it's an XY equation. Right? Or like write the equation as if it's an XY equation. If I do that, then what I have is sigma B is equal to sigma A minus S sub y, right? If I think of that as being a sort of an XY equation, I could solve it out like this. And that's basically an equation in slope-intercept form, if you will, right? What's the slope? The slope, generally speaking, is the coefficient of the x variable once you write it in the slope-intercept form like I just did. So what's the slope in this case? 1. And what's the intercept? Okay, you're close. It is, Sy is the right, magnitude, but it's negative Sy. Okay? So what we see there is that when we have sigma A and sigma B having opposite signs, we can plot something down here that is at sigma, or negative Sy, I should say, like this. And that would draw a line going like this. And what we're saying there is that as long as we're inside of here, we don't predict failure. Okay? So far, so good? All right, now let's go to my last case. All right, last case is one where we've got my two in-plane principal stresses. Okay, maybe I'll call it sigma A and sigma B, along with the 0 one, and I don't need to necessarily belabor this one. If I draw my Mohr 3-circle diagram, it's going to look something like this. And so what's my maximum shearing stress? Okay. Yeah, so sigma B, really I would probably say minus sigma B. Okay. Over 2. And we're going to say that that's equal to what? Okay, SY over 2. Okay, sigma B is going to have a negative value to it since it's compressive, and so the negative I put in front of sigma B, it really just sort of reverses that back to positive so that I can compare it with the always positive SY. Does that make sense? Like whenever we talk about an SY, we always talk about it as being a positive number. Okay, so anyway, my point with this is that all this does is it fills in kind of the backside of this square, or bit of this figure, into another square like this. And if I wanted to, I could also say we could fill in this top side like this. And if we're plotting, you know, all the different possibilities that we could have for sigma A and sigma B, okay, this kind of gives us an envelope of where we are safe. Okay, meaning we don't predict failure, right? And out here where we have failure. All right, how do you think a factor of safety might come into all of this? Okay, well let me ask you this. If you're right up on the edge of this thing, right, you have a state of stress that's maybe right there. Are you closer to failure than if you, say, have a state of stress right there? Okay, so we'll just go ahead and I'm going to give you this idea of you can plot what are called load lines on this set of axes, and what you basically do for a load line is you say, when my part is being loaded with a certain amount of force, I'm going to plot maybe my in-plane principal stresses as a point on here, and I'm going to think about a line extending up to that point. Especially when you're talking about systems that are loaded with only one force, okay? This is very useful because if you double that force, right? If you have a system that's only loaded with one load and you double that load, what usually happens is this point will move to some location that will double the length of that load line. Okay? Does that kind of make sense? Like think of if you load just a uniaxial, specimen, you load it up to half of the yielding strength, right? And then that's a certain amount of load. If you double that load, that force, then what will happen to stress? It'll double. That will cause the length of this load line to double, okay? And then you might reach to that point where it would fail. All right, so those are some ideas there, but what is always the definition of a factor of safety? Okay, factor of safety is basically a stress that causes failure over what? Applied stress, all right, or working stress is sometimes what we call that. Okay, so what would that look like for, let's say, case 1? Okay, what I would basically say is that for case 1, my factor of safety is going to be equal to sigma A, reverse that, SY over sigma A. SY would be the stress that causes failure. Sigma A is the stress it's actually experiencing. I mean, I could divide both of these by 2. I could say that divided by 2 and that divided by 2. Then I'd be talking about actually the shearing stresses, right? But those divided by 2's would cancel out, right? And I end up with a statement of what my factor of safety is going to be. And by the way, in this text, they typically use a letter N for factor of safety, in case that's confusing. So I'm going to start using that. What about for case 2? What do you think that one's going to be? Okay. Sigma A minus sigma B. Oh, and again, that's in the denominator. Excuse me. I keep reversing those. SY in the numerator, sigma A minus sigma B in the denominator. Easy stuff, right? I'm sure we will grow to love this. Okay? All right, so let's get into our example problem. It's just going to be kind of the same as case 1. The question was just, what's the factor of safety for case 3? What do you think it would be? Whoop, n sub y, right? Again, S sub y over what? Yeah, negative sigma b. Now be careful with these, right? You want to always make sure that you're taking the larger of the two in-plane principal stresses, larger kind of absolutely, right? So if you're in the negative direction, you want to take the one that's more negative, right? And then you'll multiply by a negative there so that you compare it with a positive value that you always have for SY. Okay? I would say try not to overcomplicate it. It's a pretty simple thing, really. Okay, here's the problem we're about to work. All right, it says shaft ABCD is composed of 1010 hot-rolled steel. A belt applies the forces shown on pulley B, and gear E reacts on gear D to keep the shaft in equilibrium. Shaft ABCD, that is. Okay, neglecting stress concentrations and assuming negligible widths of the gears and pulleys, let's use maximum shear stress static failure theory to evaluate a factor of safety against yielding at the critical location of this shaft. For part A, let's do that where we assume tangential interface force between gears D and E. Okay, what does that mean? What does tangential mean? Think of a tangent line, right? It's basically that line. If I was going to draw it on here, I'd probably draw it something like this. We're saying that if there's a tangent line between these two things, we're saying there's a tangential force that exists between these two gears, D and E, and that's what's going to keep it in equilibrium. Okay? So basically, like, what direction would that force be applied? Okay. If there was no force acting on gear D, what direction would this shaft want to turn? Kind of toward the direction of the 80 pounds, the direction that 80 pounds is pulling, it would try to go that way, right? Because it's more of a force up there. So we have to react against that. And so I would say it looks to me like that force would be applied something like this. Okay. And I tell you what, I'll go ahead and give that a name. I'll say that's F sub T, where T stands for tangential. Right? And so that force is applied to gear D, and that's what's going to keep this shaft in equilibrium. Okay. For part B, we'll get to that in just a minute. It turns out that with real gears, you have more than just a tangential force being applied between real gears. Real gears have what's called a pressure angle that exists between them, and that creates not just a tangential component of a force, but also at the same time a radial component of force. And that complicates this just a little bit when you have to consider both of those as opposed to ignoring the radial component. With me so far? Okay, so what do you think we want to do first for part A? Let's think about this. What is it that's causing stress on shaft A, B, C, D? Does it have any, let's start maybe here. Does it have any axial stress in it? Okay, we're not worried about axial stress, right? We don't have axial forces acting along the axis of shaft A, B, C, D. So that's one we don't have to worry about. What else do we have potentially? Say what? Torsion. Where does the torsion exist? Okay, we are applying some torsion at B, and if let's say at A and at C, let's say those bearings are totally frictionless, which we generally assume unless we're given some information to the contrary, right? So if A and B, or A and C, I should say, if bearings A and C are frictionless, then does segment AB carry any torsion? No. Segment AB carries no torsion. Okay. Where does it carry torsion? Basically, between B and D, right? We apply torsion at B, and we react it at D. Okay, so it's carrying torsion from B to D. And so we've got a stress, a shearing stress induced on the outer surface of the shaft that exists all the way from where B is located to where D is located, right? Now, that shearing stress induced by torsion is going to be everywhere the same, all the way along that length. I don't have any changes in size, right? Same diameter all the way through there, and I've got the same amount of torque that exists all the way from B to D. So that's just a constant amount of stress I'm going to have that will exist between B and D, okay? So do you want to figure that out first? Okay, I think that's a good idea. How do I figure that out? How about I sum moments around the x-axis? Okay, what does my equation look like if I sum moments around the x-axis? Okay, I'd say maybe negative 80 pounds times what? 3 inches, because that's the radius of pulley B, right? What else? Plus 20 pounds, also times a 3-inch radius for pulley B. What else? Okay, plus Ft for that tangential force that is applied on the outer surface there of gear D. And what's its radius? 2 inches. Okay? And if I solve all this out, I end up with F sub T being equal to 90, I believe I calculated earlier, 90 pounds. Okay? But that's not torque just yet, right? What's the torque that exists from B to D? I'll maybe call TBD. Right, 90 pounds. Basically what I'm going to do is multiply again by the radius of the gear where that 90 pounds is being applied, and that's just going to be equal to 2 inches. 180 inch-pounds. Okay, what can I do with that? Okay, I can find shearing stress with that torque that exists between B and D. How do I do that? Okay, TC over J, someone says. And what that looks like is 180 inch-pounds. What's C? Okay, half of 0.75 inches. All right, let me slide down a little bit here. And what's J? Okay, if you don't remember it, you can look it up, but it is pi over 32 times, if this is a solid shaft, which it is, right, it's times 0.75, which is inches, which is the diameter, raised to what? Raised to the 4th. Okay, and if I punch all of this in, this gives me 2,000 173 psi. All right. That's a nice little warm-up. Is that the hardest part? Someone says probably not. There's probably more. Okay. So we figured out that's one of the places that, or one of the ways that stress is induced in this shaft. And it only is induced from B to D. Maybe I'll put that right here. From B to D. Okay. But what else might induce stresses in this shaft? Like what other effect is going on? Okay. Think of it this way. Is that shaft also acting like a beam? It sure is, right? It is also acting at the same time as it's carrying this torsion, it's also carrying flexure. And when we have flexure, what's our formula we typically use for the maximum stress due to flexure? MC over I, right? And C and I are not the hard parts in MC over I. What's the part that's a little more tricky? Right, finding that maximum bending moment, okay? So what direction should I be looking at this to think about kind of the, maybe I'll ask this, what's the axis it is bending around? The z-axis is the axis it might be flexing around, meaning it's moving in the xy, right? If it's flexing around the z, then it's moving in the xy. Okay? So I'm going to draw this maybe a little bit funny here. Let me draw it, I don't know, this just makes more sense to me to show it this way. Here's the shaft. And I'm going to try to keep it oriented pretty close to how it's oriented on the page. What's the net effect in terms of like the force in the y direction coming from the belt forces on the pulley? Okay, we've got 100 pounds. And I tell you what, I'm going to show this y going this way and this x going this way. I think that'll be easier to see because it's like we're looking at it from the top. Okay? So let me say I've got this 100 pounds pulling down like this because that's the combination of the 80 pounds and the 20 pounds from the belt forces on that pulley. Okay? What other force can I say that I've got on here? All right, I've got a 90 pound from F sub t, okay? And what keeps this thing from moving? Okay, the supports. Now let me give you a little trick you can kind of use here. If I don't do something else with my supports, what direction will this want to spin? Like if I didn't have supports and I'm looking at that plane, what direction would it want to move? Okay? Counterclockwise. That means that my supports had better react against that direction, like that rotational direction. So if I want to be kind of slick about this, I can properly choose the directions of my reactions so that I come up with positive values. Right? And sometimes that's helpful, right? You don't have to do that, but that's sometimes helpful and might make your life a little bit easier to not have to have negative values. So what direction should I maybe show my reactions? Okay, so this one here, I might want to show down like this, and let me call that RCY. Okay, what about at A? Yeah, it probably would be better to show that one pointing upward. I'll call that RAY. Okay. Furthermore, I know some more about this. It's 8 inches to this location, right? It's 10 inches to this location. It's 3 inches to this location. Okay? And what can I do with that figure? Okay? I would sum moments first, right? What am I going to do by summing moments? Maybe some moments around A. Tell you what, I'll do it this way. This is actually moments around the Z passing through A, right? Okay. What do I have creating moments around A? Okay. And that 100 pounds that I have acting around A would actually kind of be in a negative direction, right? Okay, 100 pounds times 8 inches. What else? Times, okay, RCY times 18 inches. Okay, then what? Plus 90 pounds times what? 18 plus 3 is 21 inches. Anything else? This is equal to 0, so my reaction at C in the y direction is going to be equal to what? Well, probably can't do that in your head, and I don't want to spend time punching it in. I got 60.56 pounds. Okay. What else do you think we might want? Okay. We might want RAY. And maybe the quickest way to get that is to sum forces in the y. Okay. Minus RAY plus 100 pounds plus RCY. RCY is 60.56 pounds, and then minus 90 pounds. Okay. And all that's equal to 0. Out of this, I get RAY is going to be equal to 70.56 pounds. So what do I do with all that? Well, there's some ways that you can think about doing this, but the best way in my mind to get a complete picture of what's going on with the bending moment is to do what's called a shear and bending moment diagram, right? So the way we do that is we don't have to be super worried about that. This is actually a pretty easy shear and bending moment diagram to do. Okay. The reason I say that is we don't have like distributed forces here, right? RAY is just 70.56 pounds, right? So the general shape of the shear diagram here is going to go up by 70.56 pounds. Okay, this is V in pounds. Okay, 70.56. What happens with 100? Drops down. 100 minus 70.56 gives me negative 29.44. That's going to extend over to where RCY is located. What happens there? Drops by another 60.56. And that gives me what? What should it give me? Hopefully it gives me negative 90 down there, right? And it does. Okay? So there's my shear diagram. What do I do with the shear diagram? It gives me the tools I need, or the information I need to draw a moment diagram. Okay? And remember, the value on the V diagram is equal to the slope on the M diagram. Right? So that tells me that I have straight lines on my M diagram because I have constants everywhere on my V diagram. Right? So I have a straight line that goes up to here with a positive slope. Then I have a relatively shallower downsloping line followed by a pretty steep sloping downsloping line. So that's going to be the basic shape of my M diagram, right? I can tell just by looking at what the V diagram does. What is the only stuff I really need to know here? Okay. What is that highest point? That's all I really care about, right? And where does it occur? That's actually maybe another good piece of information to note, right? I need to know where does it happen, right? So it happens right there at the pulley B. Okay, how do I figure out what the value is? Okay, the area in that little rectangle right there tells me, if I take the area of that rectangle, it gives me the value of that point. Okay, 70.56 pounds times 8 inches. Okay, maybe I'll just write that right here. 70.56 pounds times 8 inches is going to be equal to 564.48 inch-pounds. All right? And what do I do with that information? I'm ready to do MC over I, someone suggested, right? So my stress now is going to be equal to that moment, 564.48 inch-pounds, times, okay, C is again the radius, which is again 0.75 inches over 2. And what is the I value? Okay, it's almost like the J value. It's just a denominator here of 64 instead of 32. Everything else is the same. Still use 0.75 inches to the 4th for that I value. All right, and when I calculate all of that, it gives me 13,629 psi. Okay, this is from bending. Okay, I'm now going to need to combine that in some way with the value I had a second ago from torsion. Right? Those both contribute, at least in the segment from B to D, right? Both of those are going to contribute, and really, since I'd really just figured out what the bending stress is at B, right? That's the location, that's my critical location, and I need to figure out what my maximum shearing stress is at that location so I can determine what a factor of safety is going to be. You had a question?
What we just found, that was the maximum flexural stress, right?
We just found the flexural stress at location B, right? And since I kind of made that statement up there and I said, we're going to assume negligible widths of the gears, right? What that says is I'm not going to try to split any hairs and say it's going to be a little bit different because of the width of the gear to one side or to the other. We'll just say it's going to be about the same on either side as long as that gear is not too wide. Okay? All right. Well, what do I do next with this if what I'm trying to do is come up with a maximum shearing stress? Or, actually, you know, if we want to use the equations that we just talked about, we really need my in-plane principal stresses, right? So let's think about where is that element of material that's experiencing these two stresses. Where is it? I mean, we said location B, but let's get more specific. Okay, it'll be on the outside surface of the shaft. That's good. What else? Do we know, like, that patch that's going to have our worst case stress, do we know if it's parallel with something? Okay? Think of it this way. When this thing is experiencing these bending moments, right, I would say it looks like this shaft is going to be doing something like this, if you think about how it's going to deform. Okay? When it's doing that, think about the patches of material that have to elongate and which ones have to compact in order to make it stretch like that. Does that make sense? And keep in mind, we're looking at the XY plane right here. All that being said, I would say there's a little patch of material. We can't see it because it's being obscured by this pulley, but it's right in here somewhere. If I could have X-ray vision and look through the middle of that pulley, I would look at, maybe I'll draw it this way and say, here's the pulley, here's the shaft, and let's say that I'll tell you what, I'll look at this from another perspective and say, let's say that this is the Z direction, and this is the X direction, and this is pulley B. Where's the patch? It's right there. Okay, with me? Because this is important to kind of, make sure mentally we know where we're talking about. That's where our worst case situation is going to be, because that little patch of material right there is not only going to carry torsion, it's also going to carry flexure at its maximum. Okay? Okay, wonderful. Now let's actually try to figure out what that patch of material looks like in terms of the stresses that are on it. And I'll tell you what, I'll draw it this way. Right? Here's the little patch of material. A second ago I drew it where I showed the Z going this way, so I'll do that again. There's Z, and there's X. Okay? The flexural stress, where's that applied? This way? Okay, and that flexural stress is going to be 13,629 PSI. Okay, now what about the torsion? Okay, it's a shearing stress, and think about this. The direction that the 80 and 20, kind of that torsion acting on B, it's going to try to drive the left side of that patch that way. Right? Whereas the reaction from FT is going to try to drive this side of the patch that way. You with me? Okay. So I'm going to put those on here like this and say there's a shearing stress going that way, one going that way, and the way I complete that out is by showing my stresses like this on that patch, and the value of that shearing stress is going to be 2173 PSI. How do I draw a Mohr circle off of that figure? Okay. Well, I'll tell you what I'll do first. What is the standard orientation if I'm talking about Z and X? Okay. So I probably need to put X up here and Z down here. Right? That's the standard orientation of a piece of material. If I change like that, what's going to happen with these, these values? Okay. Yeah, so I'll end up with a stress along the X direction still of 13,629. All I'm doing is rotating this, by the way, just rotating what I had before, 13,629, going that way. And what do I do here? Right, something like this. Okay, and that's going to be 2173 PSI. I'm just trying to draw it in its proper orientation so that when I think about doing a Mohr circle diagram, I get it right. What does Mohr circle look like? Okay, I will plot over here I will plot a 13,629. Okay, and on that, where would I plot my shearing stress on that line? Okay? Yeah, see how it rotates counterclockwise on the face where the 13,629 is being applied? So I plot it down here, and I call that value 2173 psi. And what about my other line? Other line's at 0, right? And so then on the 0 side, I would have a positive 2,173 psi. That would be my little state of stress. And what would the circle look like? Something like this. I don't really even care for this problem what the circle looks like exactly. What do I care about? Maybe my principal stresses. And I would say this one's going to be sigma 1 and this one's going to be sigma 3. Right? Because sigma 2, it's plane stress acting on that little patch, so sigma 2 is 0.
Why are you explaining why you call it sigma 2 and not sigma 1?
Okay? Anytime we're using that, naming convention of 1, 2, and 3, we always make 1 being the most rightward on a number line and 3 the most leftward. And in between, you've got the other one. Okay? So I'm going to call that sigma 1 and sigma 3. And what are those two values? I'm going to say sigma 1 and 3 are just going to be equal to 13,629 psi over 2 plus or minus the square root of 13,629 psi over 2 squared plus 2173 psi squared. Why do I know that so easily? Okay. What I really am doing is the first term finds the location of the middle of that circle, and the second term is finding the radius of the circle, right? Which you can think of that radius as having, you can find it with Pythagorean theorem based on a little triangle right there where one side of the triangle is 2173, and the other side of it is half of 13,629. Right? So I don't even need to look up any formulas. I can just look at the geometry of Mohr Circle, and I know what to do with my, to find my principal stresses. Okay? What's sigma 1? I tell you what, I'll spare you. I trust that everyone can punch these values in. What it ends up giving me there is 13,967 psi. For sigma 1, and sigma 3 is going to be equal to negative 338 psi. You keeping up? Okay. What now? Okay, we can find the maximum shear, or we can just go back up here and say, what case do I have? From all these cases that I was looking at a few minutes ago, what case do I have? I have a case 2. If I want my factor of safety, I just need to figure out the stress that causes yielding and divide by the difference between my two in-plane principal stresses, which I now have. Right? So I would come back down here and say that my factor of safety, n sub y, is going to be equal to, I haven't looked that up yet. The material that we had looked at a second ago was a 1010 hot rolled steel. There's a table in the back of the book, table A20. Okay. And in table A20, it says S sub y for 1010 hot rolled steel, that's what HR stands for, is 26 KSI. Okay, so when I take that down here, I would say 26 KSI is 26,000 PSI. I'm going to divide this by 967 PSI minus a minus 338 PSI. Okay, and this will give me a factor of safety of 1.861 for that problem. Now, not to disappoint anybody, but why is this incomplete? Okay, I know where. Okay, I did part A. Okay, might go back up here and say, okay, that's interesting. We assumed a tangential interface force between gears D and E. What has to change if I need to now consider a pressure angle of 25 degrees? Okay, let me show you what happens. I now need to also think of a force acting this way. And I'm going to call that one FR. Okay? How can I tell the value of FR? Okay, think of it this way. The combination of these two forces is the total force that's acting right at that location. I would just call that F. This angle right here is my pressure angle, right? 25 degrees. So what's FR? Okay, and let me do it this way. Think of tangent of 25 degrees. This is going to be equal to the opposite over the adjacent, right? Which will be FR over FT. So FR is equal to FT tangent of 25 degrees. Okay? So what I tell you what I'm going to do here is I'm going to slide in. Hopefully this works. I'm going to slide in right here and say FR is going to be equal to FT, which was 90 pounds, is that right? Times the tangent, 25 degrees. And what will that give me? I have it calculated here to be 41.97 pounds. Okay? Now here's the thing. FR doesn't do anything to mess with my torsion. Right? You see that? Because its line of action passes through the axis it would be trying to create torsion around, right? So since that line of action passes through that axis, it doesn't do anything to twist that thing. But what does it do? It creates another plane where this shaft will start to flex. Okay? So what we need to do is figure out what happens in that plane. Okay? So let me draw it. We're going to do a diagram similar to the one that we just did here, where we look at that shaft, but this time we're going to look at the shaft on another set of axes, right? Because FR okay, is going to flex this thing in the xz plane, right, which will be moments around the y. All right, bending moments around the y will cause flexure in the xz. With me so far? Okay. And so I need to actually show that on here as a downward force, right? I tell you, I'll put up here, this is z, this is x, and I have this downward force here of 41.97 pounds. Okay? Where else can I have reactions? Okay, and if I draw those the correct directions at A and C, let me call this one RCZ, and I'll put this one downward like this, RA, RAZ. Now, I could, if you wanted me to, sum some moments and figure out what those reactions are. Is that the best use of our time? Okay, so if you'll trust me, I will tell you that RCZ is 48.96 pounds. And RAZ ends up being 6.99 pounds. Okay, so what? What do I do with that? Okay, what I might want to do is think about a shear and bending moment diagram. How will this look? Okay, I've started out with a relatively small negative value here. I'm going to jump up by a relatively larger value and come over here and come down. What are these two values? It's at negative 6.99, and up here this is going to be equal to 41.97. What after that? Okay. This is my first one there was shear. This bending moment, what do I do with that? Okay. It's going to be negative sloping downward like this, and then positive sloping upward like this. How do I figure out what that value is right there? Okay. This was 3 inches, remember. Okay, so that value down there is just going to be equal to 3 inches times 41.97 pounds, right, at that point down there, which that ends up giving me negative 125.91 inch-pounds. Let me ask you this. Is that the critical location I found the first time? So do you think it's for sure the critical location overall? It might be, but we're not sure. We got to check 2 places, because this now, for this case, this might be the critical location, right? And so I've got to think about checking that perhaps, but what's the other spot that I might need to check? There's another location here, even though nothing happens on this diagram 8 inches from one end, it's still an important place that I might need to check. Okay, what's my bending moment there? Okay, I would say it's going to be 8 inches times 6.99 pounds. Okay, and that ends up giving me negative 55.96 inch-pounds. Okay, and that's at this location right here. You might be kind of, wondering, what do we do with this now? Okay, you might not be expecting this, but you can combine two bending moments in perpendicular axes, around perpendicular axes. You can figure out what the overall bending moment is by doing what, you think? Remember, moments are vectors. And we got two perpendicular vectors, and I want to figure out what's the overall net effect. You figure out the magnitude of taking those two perpendicular vectors and combining them together into a resultant. How do you do that, you think? Because keep in mind, you know, this bending moment that I just found is 55.96 inch-pounds, right? That is around the y-axis, right? Y-axis is sticking out at us, okay? The one I had before, this 564.48 inch-pounds, that one was around the z-axis, right? So it should be legitimate for me to combine those by taking the square root of the sum of the squares. Okay? That's one of the places it could be, right? I could have my max overall bending moment could be the square root of 55.96 inch-pounds squared plus 564.48 inch-pounds squared. And when I calculate all of that, it gives me an overall bending moment of 567.25 inch-pounds. Okay? I mentioned a second ago there might be two places you need to check. The one I just checked, okay, that's that one right there. Where's the other place I might need to check? Okay, and since I'm really running low on time, I'm going to just tell you that that bending moment there, overall, is going to be equal to 297.91. inch-pounds. Again, calculated the same way, right? This is the resultant of both diagrams. So which one is my maximum? Okay. This one is. Now, what do I do with that? Okay. There's no difference really. Let's just chase it through conceptually. Right? Now I have a different maximum bending moment. What did I do with the bending moment when I got down here? It went right there, changed my flexural stress. Okay? My new flexural stress for part B ends up being 14,032.4 psi by plugging in 567 in there instead of 564, basically, right? Then where do I chase that from there? Okay, I change this value, right? And that changes my principal stresses for part B to, excuse me, I think I may have misstated something earlier. This one up here, I was looking at the wrong number. This number wound up being 13,695.9 psi. And this down here for part B was 14,032 psi. And sigma 3 was negative 336.5. PSI. Okay, and I'll let you check that out if you want to try to run those calculations yourself, but it's the same process. We just changed 13,629 to 13,695, basically, 0.9. And for part B, for my factor of safety, it ends up being 1.809. Okay? It changed it by having to take into consideration both planes of bending of that shaft. Okay? I know we're really short on time here. If there are any really quick things that don't make sense, I'd be happy to try to address them. Otherwise, we can call it a day. Yes?
Is that something we shouldn't do because it's less than 2 times the factor of safety?
He wants to know if should we let this fly because it's less than 2 times factor of safety? What does the textbook say? Textbook says we don't try to give you guidelines about factors of safety. That's supposed to be based on your experience and knowledge of the field you're working in. Okay, I'll see y'all next time.